This video is about exponential equations. For our notes, we're going to start with what's called or known as the exponential property, which is this. If we have a to the x equals a to the y, then that implies, okay, so this symbol means implies. It implies that x must equal y. In other words, the exponents must be equal if they have matching bases and both sides are equal. We're going to depend on that property and some other tricks and skills to get through these kinds of equations. We're going to also list out some general strategies or options for solving exponential equations. These are in no particular order, but one option is to write both sides of the equation as a power of the same base, then use the exponential property, which we just stated above, and solve. Secondly, we might have to convert to logarithmic form and solve. We've practiced that already when understanding the definition of logarithms and how it relates to exponential expressions and equations. Or thirdly, we may need to take the logarithm of both sides and use the laws of logarithms to solve. Or, fourthly, we may need to use a substitution to turn it into a quadratic or rational form, which would take us back to those types of equations we've already solved. Or lastly, we may need some creative combination of these options above. This is the one that can be most frustrating because it seems like there's no, one standard way you do it every time. And that's true. That's why this is a creative combination. But I think the best way to understand what the options might be in that case is to see examples, which is exactly where we're going next. Let's consider our first example where we want to solve an equation that is listed as 4 to the power of x minus 1 equals 1/8. Now, in this scenario, there's actually not only one strategy that could be applied, but if you take a look at the way an equation is set up originally and find that the left and right side of it both contain numbers that could be written as the same base to some power, that might be a good hint to try to use that strategy. And it doesn't always work, so when you take numbers like 4 and 8, which are both powers of 2, that's a pretty good hint that we might want to try that. So let's just say here, try same base to a power on both sides. That same base for 4 and 8 is actually 2. So what I mean is we're going to write 4 as 2 squared. I'm going to keep the power of x minus 1 that it had originally and consider that the left side. Now on the right side, my whole point is to write that side as the same base, which is 2, to some power. Well, you can kind of guess and check your way through this, and you'll find that -3, if it's the power of 2, would turn this expression on the right side into 1/8. 2 to the -3 power is 1/8. So now that we have both sides written with base 2, we can work with our exponential property. Let's go ahead and simplify a little bit. On the left side, when you have the squared for the power of 2 and then the x minus 2, those powers will actually end up being multiplied together, which means we really have 2 to the 2x minus 2 power, and that's just using the old laws of exponents. On the right side, we'll still just copy down 2 to the -3, but now once we clearly have both sides written as some power of the exact same base, in this case 2, then we can take their exponents and just set them equal. So this would become 2x minus 2 equals -3. And now it's a much simpler algebraic equation to solve. If we add 2 to both sides, we'll simply get 2x equals -1, and then divide by 2 to get x equals -1/2. And there we go. Now, the one nice convenient thing about exponential equations is that you do not have to search for extraneous solutions. The domain of exponential functions is all real numbers, which means any value we get for x should be just fine. Let's try a second example to solve, where this one reads 2e to the 12x power equals 17. Now, at a quick glance, you'll notice that this one probably has no hope of us doing like we did in the previous example, which is writing both sides as a power of the same base. The left side already has base e, and the right side has 17. Even if we work on that number 17 a little bit, there's no way we're going to get it written as a power of e. So we're going to have to adopt a different strategy here. And observing the numbers you have at the start is a good way to kind of point you in the right direction on which strategy to use. In this case, let's also consider that this is almost in a very simple exponential form. I could confirm that by trying to isolate the exponential factor here, e to the 12x, meaning if I just divide both sides of this equation by 2, then the 2's will cancel on the left side, and that would leave me with e to the 12x on the left side equals 17 over 2. Now, what's nice about this scenario is that it is just a simple exponential equation. Now, x is in the exponent, which is not good because we want to solve for x, and it's stuck up there. We can't divide by e to the 12th. Okay, that is not the strategy that works in this case. Rather, we're going to have to convert and utilize our logarithm definitions to get further on this. If we convert this to log form, we'll review that process. Remember, you use log base e because that has the exponent to it. Log base e of 17 over 2 equals 12x. If you review back when we defined logarithms and converting back and forth, you'll recall that this does fit the process where you just convert from one form to the other. Now you'll notice that what we have is log base e. Remember, that's really ln, which is convenient to write just for the sake of jogging our memory and understanding that that is a log base e that's on the calculator. So we have ln of 17 over 2 equals 12x, but remember, if we want x, we already have it out of the exponent now. We can simply get it alone by dividing by 12 on both sides, which will leave us with, if we go up here and rewrite, x equals, it's the natural log of 17 over 2 all over 12, and this can be approximated on a calculator. So this would be the exact form. Sometimes you need or are asked to find the exact solution. That's exactly what we just found there. It's reduced. But you could also write it in an equivalent approximation form. Utilizing the ln button in the calculator, we can just type this in pretty much as we see it. We'll say natural log, and then in the input, in the parentheses, we'll put our 17 divided by 2, which was our input that we solved for. And then we're going to divide all of that by 12. Make sure to close the parentheses at the end of the log function input, otherwise the answer will not work out correctly. So we want now to divide by 12 after closing those parentheses, and we'll get an approximation here that we can round. Let's round it to 4 decimal places, which would be 0.1783. So we now have an exact and an approximated form of our answer. As you're doing problems and practice problems, you'll often see some instructions, maybe in the, just before the set of problems that says, leave it in exact form or approximate, and sometimes it'll even say to round it to a certain number of decimal. So just follow the directions given in the problem. You'll also, though, note that in our exact form, any equivalent form of this is also okay. So in other words, I could also write in the following way, using our laws of logarithms. This is the same thing as x equals ln of 17 minus ln of 2 all over 12. So we could convert it from a log of a quotient into a difference of logs. That's just using one of our laws for logarithms. It doesn't matter really which exact form is used. You'll find different preferences from different authors and things, but both of them are actually okay. Let's try another example where we want to solve an equation. This time our example reads 2 times, in parentheses here, 5 plus 3 to the x plus 1 power, close parentheses, equals 100. So again, we're going to sift through our options. If you look at our notes above, we have several different strategies we can apply, really in no particular order. You'll take a quick look though and observe that it's probably not the case that we can write the left and right side of this as some power of the same base. We certainly have base 3 on the left side that's kind of stuck with our exponential expression. The right side does not appear to be a base 3 value, but let's work on this a little bit more before we make that determination. What I mean is, let's try to isolate the exponential expression of this equation first by dividing by 2 on both sides, so that the 2 out in front of our parentheses will cancel, and that will leave us with just 5 plus 3 to the x plus 1 power equals, on the right side, 100 over 2 would be 50, and then we can continue to isolate the exponential term by subtracting 5 from both sides. That will leave us with 3 to the x plus 1 power equals 45. So now we can revisit the idea of trying to write both sides as a power of the same base, but again, you'll probably find quickly that 45 is not a power of 3, which means there's really not a good way to go in that direction. So rather, what we'll take a look at is that we have an exponential equation with a variable in the exponent we're trying to solve for. That's a pretty good hint that we may want to apply a logarithm to this, and one easy way to do that would just be to convert to log form, like we did previously. So if we convert this to log form, we'll say log base 3, that's where the base comes, and log base 3 of 45 equals the exponent, which is x plus 1. Again, review the definition of logarithm if you're a little rusty on converting from one form to the other, but this should follow that conversion pattern we've seen before. Now, again, if we're trying to find x, all we have to do is subtract the 1 that's stuck to it, and that would cancel the 1's on the right side, which means we're left with log base 3 of 45 minus 1 equals x. So this would qualify as our exact solution, but then we could approximate it, as we've mentioned, with the use of a calculator. Now, in order to handle this logarithmic expression and our exact solution on a calculator, notice it's log base 3. There is no log base 3 button on this calculator. We have log, which is log base 10, and ln, which is log base e. But thankfully, now that we know the change of base formula, we can just apply that. So using either of those buttons, I'll just pick on ln for a second, we're going to take the natural log of the input 45 and be sure to close the parentheses for that input, and we're going to divide it by, same thing, ln log base e of the base of our logarithm, which is 3. So ln of 45 over ln of 3 will handle the left term, the log term, in our exact solution. If I hit enter on that, it'll give me an approximation. Of course, then don't forget, we're also subtracting 1 in our exact solution, so I'll do that next and get an approximate answer of 2.46497. If we round to 4 decimal places, that would be 2.4650. Let's consider yet another example of where we want to solve an equation. This time the equation reads 125 to the power of x plus 5 to the power of 3x plus 1 equals 200. Now, in this example, if you go sifting through our strategies in our notes above, you'll notice it may not fit exactly any one of those nice convenience strategies we've been using already. There's no way to write both sides as a simple power of the same base. It's not exactly in exponential form, since we have actually 2 exponential terms on the left side. It doesn't quite qualify as something that's ready to convert directly to log form at this point. So we're going to have to be a little creative. This is one where you have to think out of the box a little bit. We're going to go back and understand or borrow some basic rules of exponents and rewrite this equation in the following way. We'll say this is really 125 to the x, our first term, plus, now for the second term, recall that when you have a sum in exponents, the 3x plus 1, that would be the same thing as writing 5 to the 3x times 5 to the 1. If you just go back and review some exponent rules, that's how we can rewrite that exponential term expression. Now that's all equal to 200, but again, this still doesn't quite give us a major hint or tip on where to go. So what we're going to do is now apply another one of our strategies above. Remember, this is a creative combination of our strategies. And observe that 125 is actually a power of 5. So let's rewrite that way and see where this goes. 125 is really 5 cubed. Now you may say, I wouldn't have thought of that. Well, okay, but now that you're seeing it, you might, right? That's kind of how these problems work. You have to see the examples, do the examples, and then you'll start to feel like you can get a handle on where to go with them. So we have 5 cubed written for 125, still to the power of x. Let's copy everything else we have down here. We have still 5 to the 3x power times 5 to the 1, which I'll just write as 5, equals 200 on the right side. Now, why might we be going this way? Well, let's also observe something else that's going on here. If I simply rewrite this one more time, but in the left side where I have 5 cubed to the x power, let's write that as just 5 to the 3x power, which is really what it is, right? You'd be multiplying these powers together if they're right next to each other like that. And then if I continue, this is really plus 5 to the 3x times 5 equals 200. Okay, now we're going to have to put our algebra hat on for a second. If we consider that there is a common factor of 5 to the 3x power showing up on our left side, let's just recall some algebra that will help us out here. If I had a plus 5a, remember, just think simple algebra here, we'd combine like terms and call that 6a, right? Okay, well, the underlined terms here in orange, the 5 to the 3x, is kind of like the a in that simpler algebra scenario, which means we're going to write this as if it were a plus a times 5. This is really 6 times a, except our a value is really just this 5 to the 3x power. Okay, so let's understand carefully where this is all coming from. Remember, this is like a plus a times 5. And if you recall the combining like terms steps of algebra, it really means 6 times a. Well, there's our 6, and there's our a. So this is all really still equal to 200, which is on our right side. And remember, we're trying to isolate the x here, which means we want to get this exponential factor alone if we can. And at this point we can by dividing by 6 on both sides. That will give us 5 to the 3x power on the left equals 200 over 6. Okay, so notice now we have a simpler exponential form of this equation. Now we can just convert to log form, where we'd say log base 5, that's the base we have in our exponential equation, log base 5 of the right side of our equation. Now it's 200 over 6. Let's reduce it one step and call it 100 over 3. Same thing, right? Just reduced. And that's all equal to the exponent, which is 3x. Remember, we're trying to solve for x here, and so we can get our exact solution simply by dividing by 3 on both sides. So x will equal log base 5 of 100 over 3, all divided by 3. So that's our exact solution. Now we can turn to our calculator to get an approximate solution. And at this point, I'd like to show you a neat little trick that the TI-84 Plus calculator does contain. Maybe an older calculator, a TI-83 or just a regular 84, may or may not have this feature. But it's useful if you have the TI-84 Plus, which is why I recommend that version. And here's what I mean. Instead of using the change of base formula to handle this log base 5 of 100 over 3, there's actually a way to type that in as you see it in the calculator. And that's by hitting this math key. And then you got to go down the list, or you can just go up the list. It's actually shorter, because all the way down somewhere you'll see an option that says log base. If you hit enter and are in the newer syntax of the TI-84 Plus calculator, it actually gives you some input boxes that resemble a normal looking log expression. So notice it has log and then it has a blank for the base. We can just type in 5 and then move over and type our input as 100 divided by 3. And that expression actually takes care of our numerator. Now we want to divide all of that by 3, so once we close the parentheses, we can just say divided by 3, and then get an approximation for this value. So we could say this is approximately 0.7262. Now this exact calculation could be done even if you don't have this newer TI-84 Plus version that has this log base feature in it. You would just have to use the change of base formula, which we've done previously, and you could still do it. It's just a little more typing. Just be careful with parentheses and that. It all can be done. And so our approximation again is 0.7262. Let's try another example where we want to solve an equation. It's given as 7 to the power of x divided by 2, so x over 2 is the exponent, equal to 5 to the power of 1 minus x. Okay, if you try to run through the examples we've done previously, including the strategies in our notes to see what might apply here, you'll, I think, understand quickly that this is not a case where you can write both sides as some power of the same base. 7 and 5 certainly do not have the same base. But nor is this a simple exponential form equation. Notice both sides of this equation have an exponent with our variable x in it. So there may be a couple different ways you could go on something like this, but I'd like to demonstrate one strategy listed in our notes above where, all right, let me just recopy it for a second. We have 7 to the x over 2 power equals, and then we have 5 to the 1 minus x power on the right side. Now notice I left a little bit of space in front of the right side. Now the reason I did that is because we're actually going to apply one of our strategies above that says we're going to take a logarithm of both sides of this equation. Now you can pick any log you like, but why not pick one that's already on our calculator? So we'll just pick on the natural log. You could use that one or the log base 10, just a log. The reason I'm picking one of those is because eventually I may want to get an approximate answer to this, and already being in the form that's using on the calculator will just help at that point. Now the whole point of taking the logarithm of both sides of an equation would be that now we can apply our laws of logarithms and take both of these exponents and throw them down in front of each log expression. Applying that law would mean I can rewrite this to be x over 2 times the natural log of 7, and then that's the left side. On the right side, I'll have 1 minus x. Now, since it's two terms, I'm going to put that in parentheses. Be careful with those. That exponent's now in front, and then I have natural log of 5. Now remember, my whole point is to solve for x here. I have now two instances of it, one on the left, one on the right, which means I'm going to have to get them both on the same side. So let's go ahead and distribute our natural log of 5 on the right side. And let's rewrite this here all the way across as x over 2 times the natural log of 7 equals, now I'll have natural log of 5 if I distribute it to the 1 minus x times the natural log of 5 going into that second term. Now I want the x terms on the same side, so if I add x times the natural log of 5 to both sides, those terms will cancel on the right side. On the left side, we'll have x times the natural log of 7, really it's over 2, right? And then plus x times the natural log of 5, the new term over there, and that all equals the natural log of 5. But we want to get x alone. Notice now I at least have the two x's on the same side, and using some older algebra, we could just factor out an x, which would leave us with the natural log of 7 over 2, that's that first coefficient of x, plus the natural log of 5. Okay, and so again, you can check by going in reverse. If you distribute this x, you'll get the original terms in the previous step there. That's all equal to the natural log of 5. Okay, we're on our way. Now we want x alone, and we could get that simply by dividing by this large ugly factor, if we may call it that. It's the natural log of 7 all over 2 here, plus the natural log of 5. We're going to divide by that on both sides, so that these cancel, leaving us with just an x on the left side. On the right side, we'll have the natural log of 5 in the numerator over this denominator, which you could write probably a couple different ways. Let me show you some variety there. So this natural log of 7 all over 2, you could write that as 1/2 times the natural log of 7, right? Algebraically, that's the same thing. And then don't forget our plus natural log of 5. So you could actually call this an exact solution, or if you really wanted to get fancy, you could rewrite this as the natural log of 5 over, and then you could use the power rule backwards with this 1/2 coefficient and make this the natural log of the square root of 7 plus the natural log of 5 as for the denominator there. Furthermore, you could apply another log property and make this the natural log of 5 over, and then here's the product log going backwards, or from the sum to the product, which would turn this into the natural log of 5 root 7. And that's also acceptable, but either one of those will work just fine for an exact, any of those really, for an exact solution. But then you could get an approximate solution. It turns out that last form of the exact forms we were looking at is probably the easiest to type in the calculator. And so I'll just punch that in, hit enter, and get an approximate. Again, we'll just go 4 decimals on this and get 0.6232. Let's try another example where we want to solve. This time our equation reads 3 to the power of 4x minus 3 to the power of 2x minus 6 equals 0. So we have a couple terms where they have base 3 to some power. Now that's kind of where you want to focus for this one. If you go through all of our strategies in our notes above here, remember we're always looking for some kind of creative combination or leveraging one of our strategies here. Do you see the common base in the first two terms here of 3 to the 2x? What I mean is, let's rewrite this equation a little bit differently. Let's rewrite this as 3 to the 2x squared, and by the way, wouldn't that be the same thing as 3 to the 4x, right? Okay, minus 3 to the 2x, that's just the middle term, minus 6 equals 0. Okay, so maybe at this point you can kind of get a sense of where we're going on this. If we apply a good old substitution, we could say let u equal 3 to the 2x. And if we use that substitution, then we replace the 3 to the 2x's in our previous form here with just the letter u. This is really just a u squared minus u minus 6 equals 0. Well, that's just quadratic, which means we should try maybe even just factoring this. We'll put a u, and then maybe a minus 3 and a plus 2, just using our good old factoring methods on this one. And if we solve each of those using the zero product property, that would tell us that u equals 3 or u equals negative 2. But let's not forget that the letter u was just a substitution trick we're doing here. It wasn't actually in our original problem. So we need to replace it back with our x and resubstitute here. So instead of u, I'm going to say 3 to the 2x equals 3 for the left equation. And then on the right side, I'm going to say 3 to the 2x equals negative 2. We're just plugging the u substitution back in both equations, replacing u with what it equals. Okay, at this point, we just have now two different exponential equations to solve. So on the left side, you'll notice we have 3 to the 2x equals 3. Well, that's a pretty simple example of both sides being written as the same base to some power. Remember, 3 is really 3 to the 1, which means we can just go ahead and equate those exponents to say 2x must equal 1, which means x must equal 1/2, and there is one of our solutions. On the other side, however, we have 3 to the 2x equals negative 2. 3 and negative 2 are not going to be written as the same base to some power. So rather, let's go a different route and just try maybe converting this to a log form. We've seen this trick by now, where if we convert to the other form, we really have log base 3 of negative 2 equals 2x. Okay, now this is just converting from exponential form to log form. But we have to make a really interesting observation here, which is that we're trying to take log base 3 of negative 2. But as you go back, if you go back to the definition of logarithm, and especially when we were graphing some of these, you'll notice that's a problem. You can't actually use a negative input in a parent log function, log base 3, which means this equation doesn't have a solution to it. Now, that's okay. That doesn't mean our whole answer is no solution. We still got a solution from the first side. We're just not getting another solution from this other side. Let's try yet another example. This time we want to solve the equation given as x squared times e to the x plus x times e to the x minus e to the x equals 0. Well, hopefully the repetition of what we're looking at and listening to is a bit of a hint on this one. If we could possibly simplify what we're looking at, it might be a lot easier. Do you see the common factor all the way through of e to the x? Yeah, why don't we just factor that out? So we'll write this as e to the x, and then if you factor those out of all the terms, you'll be left with x squared plus x minus 1, and that all, of course, is equal to 0 still. All right, so you'll notice here that if you factor in e to the x out of each terms, you're left with a product equal to 0, which means we can try the zero product property, in which case we'll say e to the x equals 0, or x squared plus x minus 1 equals 0. If we look at these options further, we're trying to figure out when e to the x would be 0. Well, if you think back to what e to the x really is, it's an exponential expression. And if you think back to the graph even of e to the x, you remember the horizontal asymptote we had on the x-axis for a graph of that form, or an equation of that form? Yeah, if you do, you'll remember the function never actually gets down to it, which means this will never happen. E to the x is never 0. Now, if you want even a more clear reason to say that, you could try converting this to log form. If you did, you'd say log base e of 0 equals x, but again, 0 is not a valid input for a log function. Remember, the domain is greater than 0, which means this is not going to give us any solution, this particular side. Let's go to the other side and consider what we have, which is a quadratic, x squared plus x minus 1 equals 0. Now, this does not happen to be factorable, so if we try the quadratic formula on it, we'll say x equals negative b, which is negative 1, plus or minus the square root of b squared, which is 1, minus 4 times 1 times negative 4, and that's all over 2 times a. And then if we simplify this result, this will be negative 1 plus or minus the square root of, now put this all together, inside the root you have 1, and then really it would be plus 4, so it's just really 5, square root of 5 in that root, and that's all over 2. And then this, of course, is going to remain an irrational solution or set of solutions, so we'll just keep it as is. The plus or minus means we have two options here, but there's no way to make this any simpler, so it's an irrational solution, but one nonetheless.